In this video, we are going to talk about change of basis. That is, we're going to look at the problem. If we know the coordinates for a vector relative to one basis, we want to find the coordinates of that vector relative to a second basis. And the key is that once you know how a basis is converted from one coordinate system to another, then you know how to convert all the vectors in the space, because all the other vectors can be written as a linear combination of the basis vectors. So this is our overview slide. We will spend maybe 3 or 4 minutes looking at this slide before we go over these topics in more detail and with more example. So as I had mentioned, the problem we will be looking at is converting from coordinates relative to one basis to coordinates relative to a second basis. And the key is to know how the basis is converted. Once you know how the basis is converted, you can convert anything. And we have this first theorem, change of basis theorem, and it says if we have a basis beta, which has n vectors b1 through bn, and then we have a second basis b prime. Sometimes it's hard to see the prime, but there's a prime, b prime, which is equal to, it also has n vectors because, right, bases, once you have a basis, they all have the same number of vectors, but it's b1 prime, b2 prime, up to bn prime. So they're bases for a vector space V. Then there's a unique n by n matrix, because there are n basis vectors, and this matrix is designated P, and the arrow is backwards. So we're going to go from B, this basis, to the B prime basis here. So it's the matrix that converts from B to B prime, and the arrow is telling you which way it's converting, B to B prime. And what we do with this matrix? Well, if we want to know the vector x, the coordinates relative to b prime, there's a little prime here, so relative to b prime, then we can multiply the x vector with coordinates from b times this matrix P from b to b prime. And the columns of this matrix are the b prime coordinate vectors of the vectors in the basis b. That is, this matrix now, P from b to b prime, is equal to the b1, this vector, rewritten in as coordinates of our b prime basis, our next basis vector rewritten as coordinates in b prime basis, all the way up to the nth vector rewritten in coordinates of the b prime basis. Sorry, that was my alarm, probably not yours. So for example, if we have two bases, b equals b1, b2, and b prime is equal to b1 prime, b2 prime for a vector space V, such that we can write b1 as a linear combination of b prime, and of course we can do that because b prime is a basis. So b1 maybe can be written, for example, as 4b1 prime plus b2 prime, and our b2 basis over here can be rewritten in terms of b prime as minus 6b1 prime plus b2 prime. Then suppose we have a vector x which is equal to 3b1 plus b2. In other words, x is equal to 3, 1 with respect to the basis b. Now we want to find the coordinates of x relative to the basis b prime. So here we know how the basis vectors in B get transformed to B prime. That is, B1 is transformed by 4B1 prime plus B2 prime, and B2 is transformed into minus 6B1 prime plus B2 prime. So this is all we need to know, because now if we want to transform another vector written in terms of B, that is 3B1 plus B2, and I rewrote this, x is equal to 3B1 plus B2, then what we do is we take 3 and then we rewrite b1 in terms of b1 prime, and we write this b2 in terms of our new basis, new coordinate system b prime. So this is 3. Now b1 in terms of b prime is 4, 1, and our basis 2 in terms of b prime is negative 6, 1. So here we have our 3 times 4, 1, and 1 times negative 6, 1, which means gives us our matrix now is the 4, 1 and minus 6, 1. The next thing we'll look at is change of basis in Rn, and we've seen this actually in one of our previous videos, so we'll compare that to a basis B that has n vectors, and then our second basis will be the standard basis and we'll look at the change of basis vector. It's totally analogous. We'll look at this in more detail with this example here as well. Now that we've completed our overview, we're going to start back over here again with our change of basis, our general change of basis theorem. So again, we're doing our change of basis theorem. We have a starting basis with n vectors, and then we have a new basis b prime also with n vectors. And they both have to have the same number of vectors because we had the theorem when we talked about dimension, where that said that if we have a basis with n vectors, then all other bases also has to have n vectors. So we say we have two bases for a vector space. Then there's a unique matrix that can convert. So if we have a matrix a vector x, we can then, written in coordinates in terms of b, we can multiply by this matrix that converts from b to b prime to get our coordinates of the vector x in terms of b prime. And then it tells us how to get this matrix. The columns are our first basis vector in b written in coordinates for b prime. And then our second column will be our second basis vector in b written in terms of coordinates of b prime. And we go all the way until we get to the nth vector, basis vector. We looked at this example here, but we'll do it in a little more detail now. So let's consider two bases, beta, which has vectors b1 and b2, and beta prime, which has vectors b1 prime and b2 prime for a vector space V. And we happen to know that b1 can be written as a linear combination of our b prime bases, and b1 will be equal to 4b1 plus b2 prime. And we know we can do this because b prime is a basis, so any vector can be written as a linear combination of its basis vectors. Then second, we can have b2, we can write that as a linear combination of our b prime bases, and we find that it's equal to minus 6b1 prime plus b2 prime. And I say we find, I mean it's given to us. Now the problem is, suppose we have a vector x also in the vector space V such that 3b1 is equal to b2. So it's written in terms of basis b. So also just to be clear, then the vector x is equal to the vector 3, 1 in terms of this basis here. Now we want to find the coordinates of x relative to b prime. We are going to start just by rewriting this. So our vector x is equal to 3 vector b1 plus vector b2. And now if we want the coordinates with respect to b prime, I'm just going to write the coordinates of the vector x with respect to b prime. And now I'm just going to substitute, instead of this vector x, I'm going to substitute the 3b1 plus b2. And we want that with respect to our other, our b prime bases. But because this is linear, we can break this up. We can break this up into 3, our b1 with respect to b prime, and then our 1 times b2 with respect to b prime, which then is 3, and then b1 with respect to b prime, we're given that over here. b1 is equal to 4, 1, and then we have 1 times b2 with respect to b prime, and b2 is negative 6, 1. Rewriting this as a matrix equation, we have 4, 1, negative 6, 1 times the vector 3, 1. So this part here is exactly our change of bases from b to b prime matrix. And this matrix is not just for this one vector 3, 1. Now you can plug any vector x into here to change from bases b to b prime. And also, just to check this formula out from up here, we have the formula for our matrix to convert from b to b prime. We have each vector written from b written in terms of b prime. So again, that would be b1 vector in b written in terms of b prime. So b1 vector in b written in terms of b prime is 4, 1. So that's our first column. And our second column will be the second vector from b written in terms of our b prime basis, and that would be our negative 6, 1. So this is our second column. So that's where this formula for the matrix comes in, how it corresponds. I have this diagram here that some people find useful, and if you don't, then that's okay too. But here we have a vector x in our vector space V. We can write this vector x in terms of coordinates with respect to our basis B, or we can write coordinates with respect to our basis B prime. If we want to convert from B to B prime, we're going to use our matrix that converts from B to B prime. If we want to convert from B prime to B, we will then multiply by the inverse matrix. So it's still this matrix, P from B to B prime, but then we take its inverse. We will do more examples of this, but first we're going to look at a special case of the change of basis in Rn. So if we have a basis beta that has n vectors, b1 up to bn, then our second basis here, instead of just a general basis b prime, is going to be, basically b prime is going to be our standard basis, e1 up to en. Then, as we know, b1 in terms of our standard basis is easy to get. It's what you would intuitively say is your coordinate, but we'll look at this, an example of this. And then likewise for the other vectors. In this case, we can make our matrix P to go from our basis here, b1 to bn, to our standard basis using this matrix here. So now we'll do some more examples, both of the special case and also of the general case. Our first example is we have a basis with b1 and b2. b1 is equal to negative 9, 1, and b2 is negative 5, 1. Then we have a second basis with basis vectors b1 prime and b2 prime, where b1 prime is equal to 1, negative 4, b2 prime is equal to 3, negative 5. Find the change of basis coordinate matrix from B to B prime. First, I just wanted to write my two bases in vector form and column form. So b1 is negative 9, 1, b2 is negative 5, negative 1. b1 prime is 1, negative 4, b2 prime is 3, negative 5. Because I want to change from B to B prime, that's our problem, I need to know how the basis for B, these two, B1 and B2, is transformed to coordinates in B prime. To do this, I need to write my basis vector, my B1 and B2, in terms of B prime. So in other words, I want b1, which is negative 9, 1, written as a linear combination of b prime basis vectors, which is 1, negative 4, and 3, negative 5. And then also I need my second basis vector, negative 5, 1, as a linear combination of my b prime bases, 1, negative 4, and 3, negative 5. So these are the two linear combinations I need to solve for, and I used x1 and x2 as my first set of coordinates, scalar multiples, and c1, c2 as my second set of scalar multiples. This first vector equation translates to this matrix equation. This second vector equation translates to the second matrix equation. And then here I have the augmented matrix for this matrix equation, and I have the augmented matrix for the second equation. And I'm going to row reduce so I can solve for x1, x2, and c1, c2. But the two matrices are related, so I had one other trick just to make life a little easier, and that I have my coefficients, my 1, negative 4, 3, negative 5. I put my first solution vector, negative 9, 1, and then I put my second solution, negative 5, 1, and I'm going to row reduce this matrix here all with these two vectors at once. If you don't like this, you can solve these two separately if you wanted. But if you do solve these two matrices instead of combining it into one, you'll find you're doing pretty much the same steps in your row reduction. So I find this much more convenient. So here I have my combined matrix for the two systems, and then I have this finally in row reduced echelon form. So what you can see is that for our first system of equations, x2 is equal to negative 5 and x1 is equal to 6. So I'm going to write this here. Our first set of equations is we're going to put x1 is equal to 6 times our first basis vector, and then x2 is equal to negative 5 times our second basis vector. 5 times our second basis vector. And so here I have 6 minus 15, which will give me minus 9. I have minus 6 minus 24 plus 25 will give me 1. So that means my negative 9, 1 with respect to my first basis, right, is going to be equal to my 6, negative 5, the coefficients, in front of my b prime, or I could have read it right off from here. Similarly, for our second equation here, where we were trying to convert negative 5, 1 with respect to b prime, I can read my solution is 4, negative 3. So my final matrix to go from b to b prime is then going to be my 6, negative 5 and my 4, negative 3. And this is kind of a good statement to write at some point to remind yourself you're going from b to b prime, right? I had written that I wanted to change from b to b prime so that by the end I don't forget where I'm changing to. But to convert from b to b prime, what I did is I needed to know how a basis for b, so my basis was negative 9, 1 and 5, negative 1, is transformed to coordinates, so that's the x1, x2, and c1, c2 in b prime. So that's what all this work was. So I find this is really helpful to write out and just to keep saying and remember, because then at the end, sometimes it's easy to get confused which coordinate system you're changing from and which coordinate system you're changing to. Our next example is we have our two bases, beta and beta prime. So beta has b1 is equal to 1, negative 3, which I rewrote in column form here. b2 is equal to negative 2, 4, which I wrote in column form here. Our second basis, b prime, has b1 prime, which is negative 7, 9 in column form here, and b2 prime is negative 5, 7 in column form here. The problem then is to find the change of basis coordinate matrix from b prime to b and from b to b prime. So to convert from b prime to b, we need to know how a basis b prime is converted to coordinates in b. So this is what I did. I'm looking at my bases b prime, my negative 7, 9, and my negative 5, 7, and writing them as linear combinations of my bases in b, which is 1, negative 3, and negative 2, 4. Similarly over here. And here I just use the same scalars. This x1 is not the same scalar as this. When I solve this equation, they probably aren't going to have the same solution, but I just use the same variable names because I like x1 and x2 as my variables. So hopefully that will clear up any confusion. So keep that in mind. The fact that they're named the same, these are two different equations. I use the same variables, but they're going to have different solutions, x1 and x2. Again, like the last problem now, I have the augmented matrix 1, negative 3, negative 2, 4, along with my solution negative 7, 9, and because my row reduction is going to be very similar since they have kind of the same matrix over here, I just tagged on my other solution set, negative 5, 7. I row reduced again to row reduced echelon form, and I get the matrix 1, 0, 5, 3, 0, 1, 6, 4. So what this means is if I want to write b1, this negative 7, 9, as a linear combination of my vectors b1, b2, I would have the coordinates 5 for x1 and 6 for x2. So I have that written here. Negative 7, 9 and b prime, remember that's over here, is equal to 5, 6. In other words, 5 times b1, 6 times b2. Similarly, my negative 5, 7 over here, that's my solution. This is this vector here, and that can be written as 3, 4. In other words, 3 times my first vector from b1, which is 1 minus 3, plus 4 times my second vector from b2, which is negative 2, 4. And so the coordinates are 3 and 4 in b. And my matrix now is going to be 5, 6, 3, 4. And again, this converts from b prime to b. And actually, I wrote this as b prime to b, but your book often does it like with the backwards arrow, so I'll need the b prime here to b with the arrow going to the left. The next problem, to find the matrix to go from b to b prime, I'm going to do this two different ways for you. The first way I'm going to do this is I'm going to take the matrix from from b prime to b and find the inverse to get the matrix that goes from b to b prime. So to find the inverse of this matrix is we take this matrix 5, 6, 3, 4, and we put alongside it the identity matrix. Then we do row operations till our original matrix, the 5, 6, 3, 4, becomes the identity matrix. And since as we've been going along, we've been doing the operations, the row operations on the entire row, so we've been transforming the identity matrix to the inverse matrix. So we have our original matrix to go from B prime to B, which was our 5, 6, 3, 4, and then our new matrix that goes from B to B prime, which is the inverse of this matrix, is 2, -3, -3 halves, 5 halves. I had mentioned there was another way we can convert from B to B prime, and essentially it's the same approach that we took when we tried to solve for the matrix B prime to B. So in other words, to convert from B to B prime, I need to know how to convert the basis B to coordinates in B prime. So looking at our basis B, we have 1, -3 here, and B2 is -2, 4, and we convert them to coordinates in B prime. So in other words, we need to write these bases vectors as linear combinations in B prime. So -7, 9 and -5, 7. Again, here we have our B2 as a linear combination of B1, B2, -7, 9, -5, 7. We solve as we had before using our matrix, and we put in both B's, row reduce until we get the same matrix that we got previously over here, which is good. 2 ways to do this. So now we've covered the material for this video. I have a few additional problems for you, but since we've covered all the material, I'm going to suggest at the end of each problem statement, you pause the video and give the problems a try before you look at the solutions. The first problem is we have 2 bases for a vector space, and now instead of calling it B and B prime, I call the first basis F with bases vectors F1, F2, and bases G with bases vectors G1 and G2. Let P be a matrix whose columns are F1 written as coordinates in G and F2 written as coordinates in G. Which of the following equations is satisfied by P for all vectors V in the vector space V? The first equation is V coordinates with respect to F is equal to P times V with respect to G, or the second equation, V with respect to G is equal to P times V with respect to F. So I wrote out P in this form where the first column is F1 with respect to G and F2 with respect to G. So this here, we started with F1 and then we're converting to coordinates in G. So in other words, we're going to start in F and convert to G, or P is a function from F to G. That means we're taking coordinates relative to F. So we're given F and we produce G. Again, we're given F, we produce G. So that is what this is. We're given F, we multiply by P, and we produce G. So this is the one that's true. Our next problem is based on this example we had previously done. So we'll review that first before we come up with our new problem. So the example we had done was to consider 2 bases, B, which is equal to B1, B2, B prime is equal to B1 prime, B2 prime for vector space V. And we found that B1, or we're given that B1 is equal to 4 B1 prime plus B2 prime, and B2 is equal to -6 B1 prime plus B2 prime. And we said we had a vector x, which is equal to 3B1 plus B2. So in other words, x is equal to 3B1 plus B2. So when we take this x with respect to the coordinates B prime, it's the same thing as 3 times B1 with respect to B prime, and plus 1 times B2 with respect to B prime. So that's 3 times 4, 1, plus 1 times -6, 1. So this was our matrix, 4, 1, -6, 1. Our new problem now is to find the change of coordinates matrix from B prime to B. So what I chose to do here, what we found in the previous example, is we would go from, what were we going from? We were given B, so we're going from B to B prime. B to B prime, or B to B prime was equal to our 4, 1, -6, 1. Now we're asked to find the matrix from B prime to B. So that's going to be the inverse of 4, 1, negative 6, 1. So I put the identity matrix here. I do row equations until my 4, 1, negative 6, 1 becomes the identity matrix, and then my identity matrix will become my new inverse, which is going to be P from B prime to P. So that's 1/10 minus 1/10, 3/5, 2/5. In this video, we talk about change of basis. In other words, how do we convert from coordinates relative to one basis to coordinates relative to a second basis? And the key is once you know how a basis is converted, so if you know how this first basis is converted to the second basis, then you know how to convert all the vectors in the space, because all the other vectors can be written as a linear combination. So we have this change of basis theorem, whereas if we have two bases, B1 and B prime for vector space V, where B1 has n vectors B1 to Bn, and B prime has n vectors B1 prime to Bn prime, then there's a unique n by n matrix P that converts from coordinates in B to coordinates in B prime, such that when we take x written with coordinates in, I was looking at this because I thought this was a prime, but it's not, it's a period, such that x written in terms of the basis B multiplied by this matrix that converts from B to B prime will give you the coordinates in B prime. So the columns of this matrix from B to B prime are the B prime coordinates of the vectors of the basis B. That is, our P from B to B prime is you take the first basis vector of B and write it as a linear combination, and then you find the coordinates with respect to B prime. You do the same for the second up to the nth vector. And we did this example here. We also looked at the change of basis with the standard basis as a special case. And then we also did this example, which I'll review quickly. So if our first basis is beta, with B1 equals -9, 1, and B2 is equal to -5, -1, and our second basis is beta prime, with B1 prime equal to 1, -4, and B2 prime equal to 3, -5, we then want to find the change of basis coordinates matrix from B to B prime, or beta to beta prime. And to change from beta to beta prime, we need to know how to change the basis of beta to coordinates in beta prime. So we take our basis vectors, where is this? -9, 1 and -5, 1, and we want to write it as linear combinations of our beta prime basis. That's 1, -4, and 3, -5. 1, -4, 3, -5. So these are the two vector equations which we are trying to solve. We converted it to a matrix equation, and then just to make things short, I put my solution vector here for the first equation, and I also tagged on the second solution vector here for my second equation. I did my row operations till I got a echelon reduced form, so that now I know that my matrix now to convert is 6, -5, 4, -3. And again, that goes from beta because we were taking vectors in beta and converting them to coordinates in beta prime, so beta to beta prime. So that's it for this video. Thank you for watching.